Assalamualaikum and good day everyone. So let's proceed with the next lesson on topic 5.3, which is advanced techniques in nuclear medicine imaging. Under this subtopic, we're going to look into SPECT, okay, single photon emission computed tomography, and another one is called by PET or positron emission tomography. Now, so what is SPECT? So SPECT, as you are aware, it is another advanced technique under nuclear medicine imaging. So basically, as the name stated here, computed tomography, it applies the tomographic principles to produce a 2D NMI scan. Alright. So basically, there is a relationship between this planar nuclear medicine, or previously we know it as planar scintigraphy, as in chapter 4. Okay, so it is basically very identical to the planar X-ray imaging and computed tomography. Now, the SPECT has an improved SNR over planar scintigraphy by a factor of 5 or 6. That is because the radioactivity are not being superimposed. In terms of spatial resolution of SPECT, okay, it is not intrinsically increased compared to planar scintigraphy, and in many cases, it is actually slightly degraded. Okay, FWHM of 1 centimeter being a typical value. So what is FWHM meaning? So just in case if you don't know what it is, so basically the FWHM is the full width. Okay, this one, yeah. It is actually the full width at half maximum. Alright, so WFHM, okay, it is very related to the gamma ray, okay, gamma camera ray. So since this point we are talking about the spatial resolution, so this just a quick revision on spatial resolution, yeah. So the spatial resolution in terms of the gamma camera, okay, it is a measure of its ability to resolve small objects in the field of view. So it is can also define, okay, as the minimum distance between 2 points such that they can be pictured separately. So this is the meaning of the spatial resolution of the gamma camera. So it means that if the object's placed at a distance smaller than the resolution limit, so the image will become as a single blurred one. Okay, so it is important that the objects must be at least greater than the resolution limit. Okay, the distance should be greater than the resolution limit. Alright, so I just want to share this article. Probably you might be interested to read. Okay, this one, it is a free full text analytical and experimental FWHM of a gamma camera, theoretical and practical issues. So this is quite a good reference for you to understand more in terms of the gamma camera. Okay, now about 5 times as many counts are needed in SPECT as in compared to planar scintigraphy in order to obtain an equivalent image SNR. So SPECT uses much of the same instrumentation and many of the same radiopharmaceuticals as planar scintigraphy, and most SPECT machines can be used for planar and dynamic nuclear medicine scans. Now, the SPECT is the standard acquisition modality for imaging brain and myocardial perfusion. So we're going to look into this later on. and for oncological investigations, and it can also be used to increase the image quality of static bone and renal scans. The improved quantitation of absolute concentrations of radiopharmaceuticals is also possible because corrections for attenuation and scatter can be readily implemented. Okay, now let's have a look into instrumentation for SPECT. So the SPECT can be performed either using multi-detector or rotating gamma camera systems. So in terms of a multi-detector system, so there will be a large number of scintillation crystals and associated electronics, okay, which are being placed around the patient. So the primary advantage of the multi-detector system is it has a high sensitivity, okay, which resulting the high spatial resolution and rapid imaging. Now, however, the complexity and the associated cost, okay, makes it not widely used in the clinic. The second system is by using the gamma camera system. So using a rotating gamma camera, okay, is preferred for routine clinical imaging because it can also be used for planar scintigraphy. So the data are collected from multiple views obtained as the detector rotates around the patient. So the simplest setup involves a single gamma camera which rotates in a plane around the patient, so collecting a series of signal projections. After correction for scatter and attenuation, and it can be filtered and back projected to form the image. So basically the similar process to the previous that you have learned in chapter 4. So because the array of PMT is in two-dimensional in nature, the data can be reconstructed as a series of adjacent slices as shown in figure 16 here. Okay. So we have slices 1, 2, and 3. Okay, so the multiple adjacent slices can be reconstructed from the data recorded by different PMTs. So this is the photomultiplier tubes or the detectors. Right. So the obvious improvement to this setup is to increase the number of cameras in the system, because the sensitivity per slice is approximately proportional to the number of cameras. So if you can see figure 17 here, it shows the schematic of 3-head rotating gamma camera for SPECT. Okay, so and then this right picture here is a photograph of 2-head SPECT system. So there are 2 or 3 camera systems, okay, which are commonly used. There is also an improvement in spatial resolution, with typical numbers being 6 to 10 millimeters FWHM for 3-head systems, compared to 14 to 11 millimeters for the single head. Okay. So the rotational orbit of the camera can either be circular or elliptical. So with elliptical orbits, maintaining the shortest distance between the patient and detector for body scans, and thus achieving highest possible spatial resolution. Okay. A 360 degrees rotation is generally needed in SPECT because the effects of gamma ray scatter and tissue attenuation and the dependence of the spatial resolution on the source to detector distance all mean that projections acquired at 180 degrees to one another are not identical. Okay. A focus rather than parallel hole collimator is often used in SPECT. So this paper that I showed you just now is using, if I'm not mistaken, is using the parallel hole collimator. Okay. Now back to this. Okay, this geometry increases the sensitivity of the scan without significantly decreasing the spatial resolution of the system. The typical geometries of the collimator are either a cone beam, where the collimator holes converge to a point, or a fan beam. So we have here two types of beams. The first one is the cone beam and the second one is the fan beam. The holes converge to a line parallel to the axis of the camera rotation. And the disadvantage involved in using such collimator geometries include the increased complexity of the data reconstructions. Okay, this one you can read on. Yeah, so I want to proceed with the data processing in SPECT. Similar methods of data acquisition are used in SPECT and CT. We have here the back projection algorithms, okay, which form the basic of the reconstruction of images. But there is an important difference that the scatter and attenuation correction are required for SPECT data. So as you can see in figure 18 here, it shows the uncorrected image of a cylinder containing a uniform distribution of radiopharmaceutical. So the attenuation artifacts cause the signal intensity in the center of the image to be much less than that around the edges. So as you can see, the attenuation artifacts, okay, cause the signal intensity in the center of the image to be much less than the around the edges. So a one-dimensional projection of the data is shown at the top of the image. So this is the 1D projection. Okay, the projection also shows that the noise level due to scattered gamma rays is higher closer to the objects than the further away as would be expected. So we actually cannot see it clearly here. Okay, never mind. Okay, the main thing is that you can catch the key points of it. Now we go to scatter correction. So the geometry of X-ray beam geometry in CT scan is well defined by tight source collimation, unlike the situation in SPECT where obviously no source collimation is possible. The contribution of scattered radiation to the image is potentially much greater in SPECT. So the first step that need to do in data processing is to apply the scatter correction. So the number of scattered gamma rays varies from pixel to pixel, and so a position-dependent scatter corrections needs to be performed. So one method is by using a dual energy window detection method. So one window is centered at the photo peak with a sub-window set to a lower energy. The main window contains contributions from both scattered and unscattered gamma rays, but the sub-window should have contributions only from the scattered gamma rays. So let's have a look what does it mean by this one. Yeah. So the main window typically has a fractional width, okay, WM of 20%. That's between 126 and 154 keV. Okay, this is for the titanium 99M. The sub window has a fractional width WS of approximately 7%, centered at 121 keV. So the true number of primary gamma rays that can be calculated from the total count in the main window and the count C sub in the sub window, okay, is following these equations. Okay, and the figure 19 shows the effect of a pixel by pixel scatter correction. So this is the image and projection after going through the scatter correction. So basically we pinpoint to this one, the 1D back projection, okay, of the real image here. Now we go to the second correction, which is the attenuation correction. So there are different roles of tissue attenuation in CT scan and SPECT scan. So in CT, the reconstructed image is effectively an estimation of the spatial distribution of X-ray attenuation coefficients. But in SPECT, the reconstructed image is an estimate of the spatial distribution of injected radiopharmaceutical. Okay, and the spatially dependent gamma ray attenuation coefficients will give rise to the artifacts in the reconstructed image. So this one should be corrected as well. Okay. So in the absence of tissue attenuation, a measured SPECT projection can be represented as this one. Okay, this is the formula. So where CE, okay, is a constant which relates the magnitude of the detected signal to the actual amount of radioactive in the body. So if the tissue attenuation is included, the equation 10 here will become this one. So we have another component here, the exponent term here. So the exponent here refers to the attenuation factor for the detected photons which originated from the position XY and traveling along a line perpendicular to the scintillation crystal. So equation 11 is extremely difficult to solve analytically because it involves the attenuated inverse radon transform. And so if you ask me what is this, I'm not really familiar with this one, to be honest. And so the attenuation correction is an important part of SPECT data processing. Now, the second step in processing the data after the scattered correction is attenuation correction, and it can be performed by using two main methods. So the first one, okay, is by using the assumption of gamma ray attenuation coefficient in tissue is uniform throughout the body. Okay, so the only requirement for correction is an accurate estimate of the physical dimensions and the boundaries of the area being imaged, information which can be measured by CT scan or MRI. Okay, the assumption of a spatially invariant attenuation coefficient works well when, for example, when we want to image the brain but introduced image artifacts in applications such as cardiac imaging, in which tissue attenuation is highly spatially dependent. The second technique, okay, applies the spatially variant correction based on the measured estimation of tissue attenuation properties. So here, this measurement will use the transmission scan with tubes of known concentration. So here we already know the concentration of the radioactive, which placed at the focal line of each fan beam collimator. So the isotope I153GD is long-lived and emits gamma rays with energies of hundreds keV. So when the patient is placed in SPECT scanner and the transmission scan is performed, which detects the spatial variation of this radioactive transmitted through the patient, it will then use to estimate the spatial distribution of the tissue attenuation coefficient. Then after the acquisition of the transmission scan, the patient will be injected with the radiopharmaceutical and normal diagnostic scan is being performed. Okay, if required by time constraint, the transmission calibration scan and the diagnostic images can be acquired simultaneously by using a single GD source placed at the focal line of only one of the collimators, with one detector acquiring transmission data and the other two measuring the distribution of the radiopharmaceutical. So the effect of the attenuation correction on the SPECT image is shown in figure 20 here. So this is after the attenuation correction. Okay. Now let's talk about image reconstruction. So we understand previously filtered back projections have been done or used or applied in CT scan. So here also for the SPECT data, okay, it has been the common reconstruction method. So a Butterworth filter usually used, a low pass filter, okay, and this is basically the Nyquist sampling theorem, if you can recall back from your signal processing lesson during your undergraduate study, or probably during your masters as well, okay. And the filter used in the back projection is defined with the cutoff frequency as a function of this Nyquist frequency. So besides to filter back projection, there is in addition to that, which is iterative reconstruction methods, okay, and these iterative methods give better results than filtered back projection. Why? Because of the accurate attenuation correction based on the transmission source data, which can be built into the iteration process, okay. So iterative reconstruction is referring to the iterative algorithm which used to reconstruct the 2D and the 3D images in certain imaging techniques, okay. So you can read the points discussed here. Okay, that's all for 5.3. So basically we will not cover the PET actually, yeah. So you only need to study the SPECT only. So we move to 5.4, clinical applications of nuclear medicine. Okay, so basically okay, we have a few here, a few applications. Okay, for example, we have brain imaging, bone scanning and tumor detection, cardiac imaging, and the respiratory system. So for this lesson, for this recorded lecture, I'm going to explain on bone scanning and tumor detection only. So you need to do a homework on cardiac imaging and the respiratory system. Okay, I will inform you later about this one. So let's start with the bone scanning and tumor detection. So the whole body scanning using 99 technetium 99 phosphonates, such as this one. I don't want to say it in full, so I just say the short name one, the MDP or HMDP, can be used to detect bone tumors and also soft tissue tumors that cause deformation and remodeling of bone structure. The mode of concentration of these agents in bone is thought to involve the affinity of this phosphonate for the metabolically active bone mineral hydrous. It's difficult for me to say the chemical terms here, okay? That's why I took engineering. Okay, so pardon me if I said it wrongly, which exhibits increased metabolic turnover during bone growth. So the usual response of a bone to a tumor is to form new bone at the site or in the periphery of the tumor. For example, spinal tumors, which consist of metastatic lesions growing in the spinal marrow space, which cause the bone structure of the spine to remodel. So this results in local uptake of the radiopharmaceutical. So bone infarctions or aggressive bone metastases often show up as signal voids in the nuclear medicine scan because the bone necrosis has occurred and there is no blood flow to deliver the radiopharmaceutical to that region. So I'm not going to explain these chemical terms to you. You can read it by yourself. So just make it a quick. Okay, about the cardiac imaging, this one, you only need to do some exercise or to answer the tutorial, which I will deliver or give it to you later on. So I think that's all, yeah, including the respiratory system. Alright, about this one, the PET. Okay, since I excluded this one in the explanation of the advanced technique, so this one you can just read it on. Okay, the applications of it. Yeah, probably okay, you may not need to do you may not need to do tutorial exercise or under SPECT, but I will give you a tutorial questions for for this one, the clinical applications of nuclear medicine, or PECT, later on. So I guess that's all. With that, I end our lecture, so you can start to prepare your notes and so on, just to get ready for the final examination. I think there will be 4 questions, if I'm not mistaken, based on 4 main chapters that you have learned from chapter 2 until chapter 5. So basically it's an open book final examination, so you are free to look into the notes that we have provided to you. So I wish you good luck, and if you have anything to ask regarding